From this video, we will start the portion of electrophysics of 12th standard. The first chapter from this portion is electrostatics. In this electrostatics, first we are going to see applications of Gauss theorem. In 11th standard, we have studied what is Gauss theorem. Here also I am again going to repeat what is Gauss theorem. Before that, I will explain in short what is meant by electric flux. And then we will see Gauss theorem. Only statement of this theorem. And then we will start applications of this Gauss theorem. In your syllabus, there are 3 applications. First application is to find electric field intensity at a point due to spherical shell or due to spherical charge conductor. Second application is to find electric intensity at a point due to linear conductor like cylinder or wire. And third application is to find electric field intensity due to plane sheet. First, I will explain here what is meant by electric flux. What is electric flux? The concept of electric flux we have already studied in 11th standard. To understand this electric flux, you must know what is meant by electric line of a force or electric lines of forces. What is electric line of force or electric lines of forces? Suppose this is electric field. In this region there is an electric field. In this region there is an electric field. In this electric field, at this point, unit positive charges are taken. Unit positive charges are taken. On this unit positive charges, a force will act. On this unit positive charges, a force will act. Due to this force, this unit positive charges will move in this electric field along some path. These unit positive charges will move in this electric field along some path. This path traced by unit positive charges in an electric field are called electric lines of forces. These are the electric lines of forces. Now, we are seeing that in this electric field, electric lines of forces are present. Suppose that we have considered one cross-sectional area in this electric field. Take one cross-sectional area in this electric field. These electric lines of force will pass through this cross-sectional area. These electric lines of force will pass through this cross-sectional area. These electric lines which comes through that area will make different angle with that area. These electric lines of forces that comes through that area will make different angle with that area. Some electric lines of forces which comes through that area will make an angle of 90 degree with that area. Means some electric lines of forces will come normally through that area. The number of electric lines of forces The number of electric lines of forces which comes normally through the given area is called electric flux passing through that area. Is called electric flux passing through that area, which is given by dot product of intensity vector and area vector. This electric flux is given by dot product of intensity vector and area vector. You know what is dot product? By definition of dot product, this is E into ds into cos of theta, where theta is the angle between intensity vector and area vector. This is electric flux means what? Now after this, we'll see Gauss law or Gauss theorem. Gauss law or Gauss theorem. Gauss law or Gauss theorem. This law, Gauss law, we are going to see in terms of electric flux. The statement that is given in your textbook is in terms of electric flux. What is this Gauss law or Gauss theorem? According to this law, total electric flux through a closed surface, total electric flux through a closed surface in a medium, of permittivity epsilon. A closed surface in a dielectric medium whose permittivity is epsilon. According to this law, the total electric flux through a closed surface, see, the word is closed. The total electric flux through a closed surface in a medium of permittivity epsilon is always equal to 1 upon epsilon times 1 upon epsilon times net charge enclosed by closed surface. Total electric flux through a closed surface in a medium of permittivity epsilon is always equal to 1 upon epsilon times net charge enclosed by the closed surface. This is Gauss theorem or Gauss law, which is in terms of electric flux. In short, we can write total flux through any closed surface, it is equal to 1 upon epsilon times net charge. 1 upon epsilon times net charge enclosed by that closed surface. The proof of this theorem we have studied in 11th standard. The proof of this theorem we have seen in 11th standard. In 12th standard, we are going to see applications of Gauss law. Applications of Gauss here. Using this Gauss law or Gauss theorem, we can find electric field intensity produced by different conductors. We can find electric field intensity produced by different conductors. First application in your syllabus is first application. What is first application? Applications of Gauss law. Applications of Gauss law. First application. To find electric intensity. To find electric intensity at a point. At a point due to spherical shell. Spherical shell or due to spherical conductor. To find electric intensity at a point due to spherical shell or due to spherical conductor. See how to find this electric field intensity. Consider one spherical shell or spherical conductor. Consider one spherical shell or spherical conductor of radius capital R. Of radius capital R and center at point O. And center at point O. Take one spherical conductor or spherical shell with center O and radius capital R. Suppose that plus Q charge is given to this spherical shell. Plus Q charge is given to this spherical shell. Here, surface charge density, which is Q upon A. Using definition of surface charge density sigma, which is Q upon A, we can write charge given to the spherical conductor Q. How much? Sigma into area of that spherical shell. Means sigma into 4 pi r square. Equation 1. The charge given to the spherical shell in terms of surface charge density, it comes sigma into 4 pi r square. R is the radius of that spherical shell. Take it as equation 1. Now after this, assume that this spherical shell is taken in a medium of permittivity epsilon. Assume that this spherical shell is taken in a medium of permittivity epsilon. Consider one point P. Consider one point P at a distance equal to small r from the center of spherical shell as shown in figure. Take one point P at a distance equal to r from the center of spherical shell as shown in figure. Here we have to find electric intensity produced by the spherical shell at this point P. To find this electric field intensity at point P, first we have to construct another sphere, imaginary sphere passing through point P. First construct another sphere, imaginary sphere passing through point P as shown in figure. As shown in figure. This is imaginary sphere that we have taken passing through point P. This sphere is called Gaussian sphere. This sphere is called Gaussian sphere. This is Gaussian sphere. See that the charge enclosed by the Gaussian sphere is how much? The charge present on this spherical shell, which is Q equal to sigma times 4 pi square. Charge enclosed by this Gaussian sphere comes equal to sigma times 4 pi square. This whole spherical shell is enclosed by that Gaussian sphere. First, find out electric flux over this Gaussian sphere. Find out electric flux over this Gaussian sphere, which is closed surface. And then apply Gauss law. Then apply Gauss law to get electric field intensity at that point. To find this electric flux through this Gaussian sphere, first consider a small area element here surrounding the point P. First, consider a small area element here surrounding the point P. After taking the small area element here surrounding the point P, see the directions of intensity vector and area vector at this point P. You will find that both the vectors, they are along the radius, means parallel to each other. Intensity vector also comes along the radius. Area vector also comes along the radius. Area vector is always perpendicular to given area. In case of sphere, radius is always perpendicular to surface. Therefore, area vector will come along the radius. Both vectors are parallel. Therefore, we can write here electric flux through ds area. It is equal to E into ds. Cos theta comes 1. Why? Because theta is 0 degree here. Both the vectors are parallel to each other. Therefore, electric flux through ds area, it comes E into ds. From this we can write electric flux through Gaussian sphere, Gaussian surface. Through Gaussian sphere or Gaussian surface. If we collect the electric flux passing through different ds area on this surface, we get electric flux through Gaussian surface. This electric flux through Gaussian surface we can calculate by taking integration of this electric flux. By taking integration of this electric flux, take integration of this electric flux. Take integration of this electric flux. Now solve this integration. E is constant, therefore it will come out of integration. In integration you will get ds only. What is the integration of ds? The integration of ds comes equal to area of this Gaussian sphere, which is 4 pi square. Which is 4 pi square. Generally, in case of closed surface, instead of this symbol for integration, we use such a symbol for integration. It is specially for closed surface, which is called surface integral. You can write this symbol or symbol for integration, simply like this. Both are correct. This is called surface integral. Surface integral here comes equal to how much? Surface area of Gaussian sphere, which is 4 pi square, smaller. This is the surface area of Gaussian sphere. This is the surface area of this spherical shape, whose radius is capital R. This is electric flux through Gaussian surface. Now, apply Gauss law. Apply Gauss law. By Gauss law, electric flux through Gaussian surface. Electric flux through Gaussian surface. It is equal to 1 upon epsilon times net charge enclosed by that surface. 1 upon epsilon times net charge enclosed by that surface. This electric flux we have calculated E into 4 pi square. It is equal to 1 upon epsilon times sigma into 4 pi square. E into 4 pi square equal to 1 upon epsilon times sigma into 4 pi square. This 4 pi from both sides will get cancelled. From this we get electric intensity E how much? Sigma R square upon epsilon R square. Sigma R square upon epsilon R square. This is the electric field intensity at a point due to spherical shape. First application of Gauss law. Now, we will see second application of Gauss law. Second application of Gauss law. Second application of Gauss law. Number 2. To find electric intensity. To find electric intensity at a point. due to charged cylinder or due to charged wire. Cylinder, wire, these are the examples of linear conductors. We will find electric intensity at a point due to charged cylinder or due to charged wire. See how to find this. Take one cylinder in a medium of permittivity epsilon or a wire in a medium of permittivity epsilon. Suppose that this cylinder or wire is infinite on both sides. It is infinite on both sides. Consider that on this cylinder or on this wire, positive charge is given. On this cylinder or on this wire, positive charge is given. The wire is infinite. Cylinder is infinite on both sides. Therefore, it is not possible for us to measure total charge present on this wire or total charge present on this cylinder. It is not possible. Because this wire or cylinder, it is infinite on both sides. Though it is not possible for us to measure total charge present on this cylinder, we can measure here the charge present in unit length. You can measure charge present in unit length. The charge present in unit length is called linear charge density. If lambda is linear charge density, then we can write here lambda equal to Q by L. This implies Q is equal to lambda times L. Equation 1. This is the charge present in L length on this cylinder. How much charge is present on L length? Lambda times L. Q equal to lambda times L. After finding the charge present on this cylinder in L length, now take one point P. Take one point P at a distance equal to small r from this cylinder. Take one point P at a distance equal to small r from this cylinder as shown in figure. We have to find electric intensity produced by the cylinder at that point. To find electric intensity at point P, here also first construct another cylinder of finite length passing through point P. I am constructing here another cylinder of finite length passing through point P, which is called Gaussian cylinder. This cylinder is called Gaussian cylinder, whose length is how much? L. We already seen in L length how much charge is present. The length of this Gaussian cylinder is L. Means inside this cylinder, inside this Gaussian cylinder, how much charge will be there? Lambda times L. How much charge will be there? Lambda times L. This is the charge enclosed by this Gaussian cylinder. This is equation 1. It represents the charge enclosed by the Gaussian cylinder. Now we have to find electric flux over this Gaussian cylinder. And after finding this electric flux over this Gaussian cylinder, use Gauss law. By Gauss law, the electric flux over this Gaussian cylinder is equal to 1 upon epsilon times the charge enclosed by that Gaussian cylinder. To find the electric flux passing through this Gaussian cylinder, for simplicity, divide this Gaussian cylinder in two different parts. To find electric flux, through Gaussian cylinder, divide it in two parts. Number 1, upper and lower plane surface. Upper and lower plane surface. And second, this curved surface. First, write here electric flux passing through upper and lower plane surface. Then find out electric flux passing through curved surface. Addition of these two will give you electric flux through this Gaussian cylinder. For upper and lower plane surface, observe that intensity vector and area vector, they are perpendicular to each other. Here area vector will come like this and intensity vector will come along the radius. Similarly, for lower plane surface also you will find that area vector and intensity vector, they are perpendicular. Therefore, we can write here electric flux through upper and lower plane surface. How much? It is equal to 0. Because these two vectors are perpendicular. Therefore, electric flux through upper and lower plane surface comes equal to 0. Now to find electric flux through this curved surface, take small area element ds surrounding the point P. First write down electric flux through this ds area. To find electric flux through this ds area, see the directions of intensity vector and area vector. Here also you'll find that intensity vector and area vector both come along the radius. Therefore, electric flux through ds area. You'll get equal to E into ds. From this we can write electric flux through curved surface. It is integration of E into ds. integration of E into ds. Solve this integration. Taking E out of integration, in integration you get ds only. What is integration ds? If we cut here this curved surface and we open it, if we cut this curved surface here and open it, we get here a rectangle. We get here a rectangle whose length is equal to circumference of that cylinder. Whose length is equal to circumference of that cylinder. And weight is equal to L. Integration ds, it comes equal to area of this rectangle. Integration ds, it comes equal to area of this rectangle, which is here 2 pi r into L. Which is here 2 pi r into L. This is the electric flux through curved surface. From this we can write now electric flux through Gaussian cylinder. Electric flux through Gaussian cylinder. It is the addition of these two. 0 plus E into 2 pi RL means E into 2 pi RL. This is the electric flux through Gaussian cylinder. After finding electric flux through this Gaussian cylinder, now use Gauss law. By Gauss law, electric flux through Gaussian surface. Electric flux through this Gaussian cylinder. It is 1 upon epsilon times net charge enclosed by that cylinder. 1 upon epsilon times net charge enclosed by that cylinder. Electric flux through this Gaussian cylinder or Gaussian surface, it is E into 2 pi RL. Equate this 1 upon epsilon times net charge enclosed by that cylinder, which is lambda times L. Which is lambda times L. Cancel this L from both sides. We get E is equal to how much? Lambda upon 2 pi r epsilon. 2 pi r epsilon. This is the electric intensity at a point due to charged cylinder or due to charged wire. Next application of this Gauss law I will explain in next video.